Welcome to The Explainer. Today, we're doing something really exciting. We are taking a deep dive straight into the mind of an AI. Specifically, we're unpacking Chapter 6 of our source material, which is all about working with memory and knowledge RAG for agents. We're going to look at exactly what it takes to transform a basic, completely stateless chatbot into a highly dynamic, context-aware agent. I mean, if you've ever interacted with the system and thought, wow, how does this AI actually remember my weird specific preferences, or how is it instantly referencing a massive 500-page company document? Well, you are in the exact right place. We're going to break down the foundational blueprints for this. We'll explore how working with memory and knowledge retrieval literally changes the whole game. So let's just dive right in and figure out how we give our autonomous agents the true power of persistent memory and real-world knowledge. Here is our roadmap for today. 1. The amnesia problem. 2. How RAG solves agent knowledge. 3. Grounding, forcing the truth. 4. From knowledge to memory. 5. The architecture of agent memory. And finally, 6. Uncluttering the agent mind. All right, let's start with section 1, the amnesia problem and the limitations of LLMs. I want you to think about this foundational question for a second. What actually happens when an AI agent needs to know today's wildly fluctuating stock price? Or, say, it needs to recall a really nuanced conversation you had with it just yesterday? Well, the harsh reality is, it can't. Without a very specific, deliberately engineered framework wrapped around it, a large language model is completely and utterly frozen in time. It's stuck in the past. It operates in this purely stateless vacuum, meaning it has zero awareness of the present moment or literally anything that has happened since its initial training run finished. Think of it this way. A standard model's internal knowledge is strictly fixed. The weights and parameters that make up its core intelligence are totally immutable once that training process ends. So if your agent is built on a model with a 2025 training cutoff, it literally cannot tell you today's closing bell price, it doesn't know the weather in Calgary right now, it definitely can't summarize a proprietary PDF report you just wrote this morning, and on top of that, it suffers from total amnesia between sessions. Every single time you open a new chat window, it is exactly like meeting you for the very first time. We have to accept a hard truth here. Models are reasoning engines, they are not databases. To build a highly functional agent, we have to radically shift how we think. We have to stop relying on what the model inherently remembers, and instead focus entirely on what it can reason about when we give it the exact right context injected precisely at the moment you ask a question. That takes us to section 2, how RAG solves agent knowledge. So how do we successfully get that crucial context directly into the model's hands right when it needs it most? The answer is Retrieval-Augmented Generation. We all know it as RAG. RAG effectively closes this massive knowledge gap. It acts as the knowledge engine of our whole agentic blueprint because it allows the agent to dynamically fetch current, highly specific information from external sources exactly at query time. And the whole thing is broken down into 2 very distinct phases. First, you have ingestion, which is where external documents are loaded up, processed, and stored in a special format. Second, you have retrieval. This is where a user's prompt triggers a search through that stored data, pulls out the most relevant pieces of context, and then seamlessly glues it onto the prompt before it ever gets sent to the language model. Let's actually trace this out step by step, because it's fascinating how unstructured text becomes a searchable asset for an AI. Step 1, a source document. Let's say a massive corporate wiki is loaded into the system. Step 2, it's systematically transformed and chopped up into smaller, manageable chunks of text. This is absolutely critical because you simply cannot shove an entire encyclopedia into a model's context window all at once. It would totally overwhelm it. Step 3, a specialized embedding model takes over. It converts these text chunks into high-dimensional vector embeddings. Basically, this is the magic of turning human language into mathematical coordinates. Concepts with similar meanings get grouped closer together in this math space. Step 4, those vectors are securely stored in a specialized vector database. Then, finally, step 5. When a user asks a question, that specific query gets converted into a mathematical vector too. The database does a lightning-fast similarity search, finds the mathematical chunks that most closely match the meaning of the question, and pulls them out. The LLM isn't the sole source of truth anymore, it's now a brilliant reasoning layer operating strictly on top of this highly relevant, freshly retrieved data. Moving right along to section 3, grounding, forcing the truth. Now here's the catch. Because large language models are fundamentally probabilistic token predicting machines, introducing all this external text creates a very dangerous new problem. If they don't explicitly know something, they will naturally try to invent a really plausible sounding answer just to appease you. We call that hallucination. To stop this dead in its tracks, we have to implement a strict safety mechanism called grounding. Grounding is the practice of explicitly verifying that a model's final output strictly aligns with the retrieved source documents, instead of relying on its internal training. And there are degrees to this. Weak grounding means the generated answer just kind of generally aligns with the provided document. That might be totally fine for a creative writing assistant. But strong grounding, where every single factual claim must trace back directly to a verifiable citation in the text, is absolutely non-negotiable for high-stakes stuff. I'm talking customer support bots, legal analysis, or medical tools. There is zero room for error there. There's this fantastic quote from Chapter 6 that hits the nail on the head. The agent designer's job is to tell the model that the retrieved context is the authoritative source for this task, and that the model should defer to it. The crucial point here is that the model isn't maliciously trying to lie to you when it makes things up. It's literally just doing its job, predicting the most statistically likely next tokens. It is our responsibility as system designers to force the model to stick to the facts. We do this with really specific prompt engineering patterns and rigid systemic guardrails that leave absolutely no room for creative liberties when handling hard facts. So how do we build that guardrail in a live production environment? Well, we don't just cross our fingers and rely on a strongly worded prompt. We deploy a secondary specialized agent. The primary RAG agent does the initial heavy lifting, generating an answer from the retrieved context. But before the user ever sees that answer, it gets passed directly to a secondary grounding agent. Think of this secondary agent as a really strict editor. It looks at the exact same context, cross-references every single claim the primary agent made, and critically decides if there are any hallucinations or weird leaps in logic. Depending on what it finds, it can approve the answer, block it entirely and return a safe static response, or literally send it back to the primary agent and say, try again, but stick to the facts this time. It's a brilliant automated system of checks and balances. Let's transition to Section 4, from knowledge to memory. Now that we know how an agent acquires and verifies external facts, we need to turn our focus inward. We have to clearly contrast two concepts that sound similar but are distinctly different in an agentic system: knowledge versus memory. Knowledge is essentially what the agent reads. It's static, it's external, it's shared identically across all users, and it's carefully curated by developers. Think company manuals or a shared code base. Memory, on the other hand, is what the agent actively experiences. It is entirely dynamic, highly internal, and strictly scoped down to a single specific user or session. Memory is your running conversation history, your personal preferences, and the distinct observations the agent deliberately records about its own past behaviors over time.
But here is the absolute brilliant architectural twist. Both static knowledge and dynamic memory actually utilize the exact same underlying mechanism. When a user interacts with the system, both the external document indexes and the internal personalized databases are queried simultaneously. The results from both streams are pulled directly into the prompt augmentation stage together. This gives the language model both the broad external facts and the highly specific internal personal context, blending them seamlessly before generating an answer. The exact same retrieve then generate pattern we use to search a corporate PDF is the identical engine powering the agent's ability to remember your name, your past questions, and your unique interaction style. It's so elegant.
Which brings us perfectly to Section 5, the architecture of agent memory. When we engineer an agent's memory, we borrow a lot of terminology straight from human psychology. We use terms like episodic memories, which are like sequential life events or conversation histories, and semantic memories, which are isolated facts, concepts, and learned preferences. But let's be totally clear here. While these cognitive terms are incredibly useful metaphors for us to communicate our designs, agent memory is highly mechanical. It is a deterministic process built entirely from cold databases, vector stores, API calls, and rigid context windows. It does not organically grow like a biological brain, no matter how much it might feel like it to the end user. Let's actually walk through a semantic memory workflow to see how these mechanics operate in practice. Imagine you're chatting with an agent, and you casually say, "I really love time travel movies." A memory function runs seamlessly in the background, extracts that specific preference, converts it into a vector embedding, and permanently stores it as a semantic memory. The agent just moves on. But then, maybe 2 months later, you log back in and simply ask, "What movie should I watch tonight?" The system springs into action, converts your question into an embedding, queries the database, and instantly retrieves that deeply buried memory. User likes time travel movies. That critical piece of historical context is pulled into the prompt before the LLM even formulates a reply. Armed with that data, the agent can confidently recommend a brilliant sci-fi flick, making the whole interaction feel totally effortless and deeply personalized. Practically speaking, we have to physically separate these memory architectures based on urgency and capacity. Short-term memory, or working memory, just lives inside the active context window. It's stored as raw text and provided automatically as an ongoing message history while you're chatting. But context windows have strict token limits, and if you overload them, it gets incredibly expensive fast. That is exactly why long-term memory requires external architecture. We store those long-term items as heavily summarized text snippets or mathematical vectors, and retrieve them exclusively via semantic search using vector databases or knowledge graphs. This dual-layered approach lets the agent flawlessly recall details from months ago without constantly redlining its immediate working memory and driving your computation costs through the roof. Finally, we reach Section 6, Uncluttering the Agent Mind. So, transitioning to persistent memory brings up one last massive engineering challenge. Storing everything forever sounds fantastic in theory. In practice, it is a nightmare. Just like a human mind, an agent's memory store can become incredibly cluttered over time. It fills up with redundant info, totally unrelated details, and token-heavy noise. Let me tell you, in production-grade systems, infinite storage is not the goal. Passing thousands of irrelevant tokens into an LLM's context window is not only crazy expensive, it actively dilutes the agent's attention. It literally causes the model to hallucinate or completely miss the actual relevant data hidden in the prompt. Operational leanness and strict relevance are absolutely critical. Because of this clutter problem, we must actively maintain and prune the agent's mind. We use a few highly effective strategies for this. First is memory compression. Instead of saving every single word you've ever typed, we have a background process summarize dozens of conversational turns into a single, dense memory fact. Second, we focus strictly on extracting significant, actionable details rather than hoarding raw interaction logs. And third, this is huge for long-term deployments, we apply strict eviction policies. We actively and intentionally force the agent to forget stale facts, resolved issues, or severely outdated user preferences. By deliberately clustering similar data and aggressively pruning the noise, we ensure the agent's retrieval mechanism remains wildly accurate, incredibly fast, and cost-effective. A highly sophisticated way to manage all this complex state is by using a local knowledge graph via the Model Context Protocol, often called an MCP memory server. Instead of just blindly throwing millions of mathematical vectors into a bucket and hoping semantic search finds them, this specialized module maps the agent's entire cognitive workspace into distinctly related entities and distinct observations. So before the agent even begins planning a solution to your prompt, it proactively searches this graph for task-related entities. After it solves the task, it actively records its experience and the outcomes. Amazingly, it can even build complex cross-problem relations, noticing that a strategy that worked for one issue might apply to a totally new one. This structure gracefully handles vast amounts of data by interlinking concepts, turning isolated problem-solving events into rich, cumulative institutional knowledge that scales beautifully over time. And that brings us to the end of our deep dive into Chapter 6. We have comprehensively explored how to inject external knowledge utilizing RAG, how to force absolute accuracy using secondary grounding agents, and how to effectively build both short-term working context and long-term persistent memory. But the real ultimate art of agent engineering doesn't just lie in adding more features. It lies in maintaining a perfect, elegant balance. So I leave you with this final critical thought to ponder as you go out and build your own systems. How will you carefully design your autonomous agent's mind to scale dynamically into the future without it eventually drowning in its own endless memories? Thanks so much for joining me on this explainer, and I will catch you in the next one.